impulse momentum theory tells us that the impulse generated during an event, the integral of f dt, will cause a change in the linear momentum in a system, which will be g final minus g initial mv final minus mv initial. And it's important to understand that the impulse is from an external source. When these two wagons reach each other and collide, there will be internal forces here where the wagon in the back will exert a force on the one in the front. We'll call that F1 onto 2. And the wagon in the front will exert a counter force of F2 onto 1. And Newton's third law tells us that these will be equal and opposite action-reaction pairs. So if we do some of the forces on the system, those will cancel out. So when we're looking at an impulse here, we're not looking at any internal forces. We're looking for some external force. For example, if there was a large rock in the road, just as these two wagons collided, this one also hits the rock. Well, we wouldn't anticipate that this is going to conserve linear momentum. This wagon's going to stop suddenly, and that would be a large external force in that event. Or if we were only looking at one object, say this object in the front, it's moving along at v2, there's a collision that we don't know about. Next thing we know, we're moving at some new v2 prime, and the wagon behind would exert an impulse. F1 on 2 would now be an impulse on that wagon. So we can look for impulses on individual particles, but generally we try to make our system big enough so that all of the internal reactions will cancel out. And from that we can say that the momentum before an event will equal the momentum after. And that becomes our conservation of momentum theorem. What if the wagons were moving down a hill when they collide? We can see that there'd be an m2g sine of theta on this one, and there'd be an m1g sine of theta on that wagon. So there are definitely external forces acting on here. However, what's the time of impact here? When these collide, we're talking about a fraction of a second or so. So even though there are forces in play that are external, they don't have much time to act, so the impulse will be very small. And as such, we can assume that it's going to conserve momentum in that event. What if there were friction acting on the surface? At the instant that they collide with each other, again, we'd have a very small amount of time, and as such, then we would say that there's a very small impulse and it would still conserve linear momentum. However, if we took a rope and tied it to the rear wagon, and just as they collided, the rope went tight and then also snapped, that would be a very large external force. Even though it's a small amount of time, the force itself is quite large, and that would have an effect on the system. And therefore, we would not expect it to conserve linear momentum. In fact, if we knew the difference in momentum, we could find the impulse that was imparted to the rope by just measuring the difference of the momentums before and after that event. In general, we'll find that most collisions will conserve linear momentum. Let's take a look at the work energy theory as it pertains to collisions. And recall here that work is the integral of f dot dr, and that will cause a change in kinetic energy, which would be kinetic energy final minus kinetic energy initial. And here again, we're looking for external work being done. If we look inside the wagons here, there are forces that are equal and opposite, and the work that wagon 1 imparts on 2, there's an equal and opposite amount of work imparted back onto wagon 1. So if we look at the system, there's no external work being done, and we would say then that it conserves kinetic energy. However, what if these wagons collide and they were badly damaged in the collision. The metal was crushed. That crushing of that metal takes work to be done, and we don't get the work back. So we'd anticipate that to be a large loss of energy, and therefore we would not conserve kinetic energy. We can look at two distinctly different types of collisions, where elastic collisions will conserve momentum and they'll conserve kinetic energy. Plastic collisions, on the other hand, will conserve momentum, but they will have a gain or loss of kinetic energy. The kinetic energy will not be conserved. Examples of these would be any collisions that involve deformation, the work done in deforming the objects is a loss of energy, an explosion would impart an amazing amount of kinetic energy to the particles. Interestingly enough, it would still conserve linear momentum though. Another one would be if they stick together. Sticking together is not overly natural. It takes some kind of mechanical binding to do that. In fact, these have a special name. They're called perfectly plastic, and they're fairly common. For a perfectly plastic collision, we know they're going to stick together, and they'll move then with some common V final, we'll call it, and they've been adhered together. And it does take some form of deformation for that to occur, so we'd anticipate here that there's going to be a loss of kinetic energy as a result. However, all these events will conserve momentum, and as such we can say the sum of all the momentum before the event has to equal the sum of all the momentum after the event. So before the event we have m1 v1 plus m2 v2, and then after the event over here we have m1 v1 prime plus m2 v2 prime, where the primes indicate that that's the after the collision speed. In our case, if they stick together, v1 prime equals v2 prime equals vf, we'll call it. So we get then that m1 v1 plus m2 v2 is m1 plus m2 v final. They stick together and they behave as if they're one object at that point, moving with a common speed of vf. So that's a classic form of a perfectly plastic collision. And here we would expect that the kinetic energy before is not the same as the kinetic energy after. There will definitely be a loss of energy. In the case of perfectly elastic collisions, the two wagons will collide, and then afterwards they'll separate from each other with no damage and move off with their own respective velocities afterwards. So elastic collisions, we know, will conserve momentum and kinetic energy. Let's see how we'd solve that. So conservation of momentum and the conservation of kinetic energy tells us that the kinetic energy before, which would be 1/2 m1 v1 squared plus 1/2 m2 v2 squared, is conserved. So after the event, m1 v1 prime squared plus 1/2 m2 v2 prime squared. We're going to conserve energy, kinetic energy, and we're going to conserve momentum. Now from here, the general process, we have two unknowns usually, would be to solve for one of them and substitute it into here, and then square all of that and try to get a solution, which will generally be a second order polynomial requiring us to use the quadratic equation. But that's a lot of work, and it turns out there's a very nice shortcut that we can use here. Let me reorder these. Let me bring all the m2 information to the right hand side. Let me bring all the m1 stuff to the left-hand side. And if I do that, I'll get m1 v1 minus v1 prime will equal m2 v2 prime minus v2. We bring this term over. So our momentum equation could be written that way. And let's do the same thing to the energy equation. If I multiply through by 2 and collect all the m1 information on the left, we'll get m1 v1 squared minus v1 prime squared will equal m2 on this side times v2 prime squared minus v2 squared. And here you'll see that that's the difference of two squares. So I can write that as m1 v1 minus v1 prime v1 plus v1 prime. And the same thing on this side, difference of two squares, v2 prime minus v2 prime plus v2. And now we'll take these two equations and merge them together to see what our solution is. But again, before we just jump in and do that, let's take a careful look at this. m1 v1 minus v1 prime is parked right here. And m2 v2 prime minus v2 is right there. And since those two things are equal to each other, we can divide through by them and they'll cancel out, and we'll end up simply with v1 plus v1 prime is v2 plus v2 prime, which if I now bring the before values to the left and the after values to the right, we'll get v1 minus v2 is v2 prime minus v1 prime. And note that whatever we start with here, it'll be switched on the right hand side. And it turns out this equation is very easy to remember, and it's also quite useful. Let's take a look at it. v1 minus v2 is v2 prime minus v1 prime. v1 minus v2 represents the relative velocity of approach, and v2 prime minus v1, the difference of these two, is the relative velocity of separation. Let's give these some numbers. Let's have this be 10 meters per second and this be 2 meters per second, and let's have this be 8 meters per second afterwards, and we'll try to find that. Well, v1 minus v2 will be 10 minus 2, which is 8 meters per second. And that tells us that wagon 1 is closing in on wagon 2 at 8 meters per second. If you were on board wagon 2, that's what you would see. Wagon 1 coming at you at 8 meters per second. The relative velocity of separation is that v2 prime minus v1 prime. v2 we know is 8 minus v1 prime we don't know. And from that you can see that v1 prime will be 0. This wagon would need to stop, and the relative velocity of approach equals the relative velocity of separation. If you're on wagon 2, you see wagon 1 approaching you at 8 meters per second, and on wagon 2 you would observe wagon 1 leaving you with 8 meters per second. You would assume you're at rest and you'd watch the relative motion of wagon 1. So this equation's extremely useful in that we can use it instead of the kinetic energy equation. What do I mean by that? For an elastic event, which is the only time this is valid, step 1 would be conservation of momentum, and then step 2, use the relative velocity equation instead of the kinetic energy equation. This equation right here has a lot of squareds in it, which is a lot of work, and we can use this instead. In the case of generalized plastic collisions, where they're not elastic and they don't stick, they collide with each other and there's some deformation, but they still bounce apart. The general format would still be the same. The momentum equation is always valid, and the kinetic energy equation would not be valid, which presents a real problem in that if they don't stick together, we have a V1 prime and a V2 prime afterwards. So we have two unknowns, but only one equation, the momentum equation, since the energy equation isn't valid. So this problem would be indeterminate. However, perhaps there is a way that we can still use this equation. If we knew that this type of collision up here generally caused, let's say, a 50% loss of energy, then we could use that to bring this equation back to life. We could say that 0.5 times the kinetic energy initial equals the kinetic energy final, and then plug in all the appropriate values, and we'd have our second equation, in which case we could solve for the two unknowns that we've got. Well, rather than doing that with the kinetic energy equation, we could also then do that with the relative velocity equation that we just developed. We say that V1 minus V2 is equal to V2 prime minus V1 prime. Relative velocity of approach is equal to the relative velocity of separation. We can multiply this by E, which is called the coefficient of restitution, or COR, and this represents the loss of energy during the impact event and allows us to solve for generally plastic equations. If we rearrange this, we can take a different look at it, where we often write it as E is V2 prime minus V1 prime over V1 minus V2. And it has a range of typically 0 to 1. And let's look at each of those. For E equal to 0, we get 0 is V2 prime minus V1 prime, or V2 prime is equal to V1 prime, which tells us is our perfectly plastic sticking together. If you look at an E of 1, we get that V1 minus V2 is V2 prime minus V1 prime, which we call was our perfectly elastic event, where we have conservation of kinetic energy inside the system. So 0 to 1 goes from sticking together all the way up to perfectly elastic. And then anything in between is the family of just general equations that haven't stuck together but also are not conserving their elastic energy. Now, experimentally, the coefficient of restitution has been calculated for quite a few different numbers of materials, and it can be looked up. Here we have a family of metals, and they're all hovering around 0.9. As we move into the plastics and some of the other materials, we start to drop down to around 0.6 or 0.7. Now keep in mind there's a number of factors that also will change this, such as impact velocity, temperature, size. I mean, think about it, as the temperature goes up, the material is going to get softer, and therefore its COR would decrease. As the velocity goes up, we'd anticipate that the impact would be more destructive and more deformation might occur, and therefore we would see the coefficient decrease as well. Along with size. If there's more size, there's more inertia, and it has the ability to do a little more damage on those contacting surfaces. Glass, for example, has a very large coefficient of restitution, starting up here around 0.9. But notice as the impact velocity increases, we find that the coefficient of restitution begins to decrease down to near 0.8. So impact velocity does play a role. Here we have the coefficient of restitution for steel balls impacting a plate, where again we're starting out around 0.9 for very, very low impacts. And as the velocity of the impact increases, we see the coefficient of restitution dropping dramatically in some cases. And here we have plotted the diameter or size. So as the size increases, we see the coefficient of restitution decreasing, and as the velocity of impact increases, we also see the coefficient of restitution decreasing. So all of these play a role. And here we have a table of quite a few different materials plotted, where marble and hard bronze are fairly high, up in the 0.9 to 1 range, particularly at very low impact speeds. Steel, which one is very common for us, starts around 0.9, 0.85, but look how quickly it decreases to below 0.5. So we do see a very wide range in that coefficient of restitution E for different values. Now the coefficient of restitution itself is fairly easy to measure. If we take a ball and hold it above a steel plate, a height h, and drop it, it'll undergo a collision with the steel plate and then rebound back up a distance of little h. So the velocity at impact here, v1, will be the square root of 2gh, and v1 prime here will be the square root of 2g little h. That's the velocity it would need to carry it up to that height. And for object 2, we'll call the plate 2. If we plug that information into our coefficient equation, the plate doesn't move before or after the event. So we get that the coefficient is negative v1 prime over v1. And these are done as absolute values. So we get v1 prime over v1, which will be, if we plug in our velocity equation, the square root of 2gh over the square root of 2g capital H, in which case the square root of 2 g's can drop out, and we get the square root of h on h. So the coefficient of restitution is fairly easy to calculate. We can drop an object onto any surface, measure the initial height, measure the final height, and we can plug our values in. For example, here E would be, when I measure this, I get about 8 centimeters for here and 5 centimeters for here. So it will be the square root of 5 centimeters over 8 centimeters. The centimeters go, and we'll get 0.8 for the coefficient of restitution for that object, whatever it might be made out of. Here we have the case of a pile driver, where we have a 300 kilogram ram that is lifted 1 meter above a pile, and it is dropped, and it's observed that it rebounds by 10 centimeters and drives the pile into the dirt. Let's apply conservation of momentum to this event. So the initial speed of the ram will be the square root of 2gh, be the square root of 2g times 1 meter, which is 4.43 meters per second. And the velocity of the ram after the event be the square root of 2g times 0.1 meter, if we convert that from centimeters, which will be negative 1.4 meters per second. Now the negative is because we're calling down positive by leaving that positive here. And momentum is a vector value. We have to be very careful to flag that as negative inside the problem. And with that, we can apply the conservation of momentum, which says that mram vram plus m pile v pile equals mram vram after plus m pile v pile after. And initially the pile's not moving, it's stuck in the ground. So we have then 300 times 4.43 is equal to 300 times negative 1.4 plus 400 times the velocity of the pile after. And if we solve that, we get the velocity of the pile after is 4.4 meters per second into the ground, since it came out positive. So that tells us that conservation of momentum says that this will move at 4.4 meters per second. Now we could check to see how the energy is doing, since we don't know whether this is elastic or plastic really. So the kinetic energy before will be 1/2 m ram v ram squared, which is 1/2 times 300 times 4.43 squared, which is 2944 joules. So that's what we have going into the event. And the kinetic energy after is 1/2 m ram v ram prime squared plus 1/2 m pile v pile prime squared, which is 1/2 times 300 times negative 1.4 squared, but that's going to become positive when we square it. You can't have negative kinetic energy, plus 1/2 times 400 times 4.4 squared, which gives us a grand total of 4120 joules after the event. And if you look at that, we've nearly doubled our kinetic energy. That's impossible. What's gone wrong here? We could at first think that maybe this data is wrong, but we have to assume that somebody went out and saw this. This was lifted 1 meter in the air and dropped, and then after the impact, this rebounded by 10 centimeters. And the conservation of momentum says that this is valid. This should work like that. So what are we ignoring? What are we missing here? And the answer to this is stuck in the ground. So we have a very large impulse coming from the ground, preventing this pile from moving, and as such, that impulse says that we are not conserving our momentum. So we need a different way to solve this type of problem. If we take a look at our coefficient of restitution, our impact speed was around 4 meters per second, which is going to be about 12 feet per second. So we're going to be way out here on this end of here, and we're steel on steel. We'll be someplace around 0.5 to 0.4. For the sake of argument, let's just assume that it's around 0.5. Where we know that E is V pile prime minus V ram prime over V ram minus V pile, absolute value of, and these are always reversed. Whatever we have here is on the opposite side. The pile was initially not moving, So we end up with VRAM times E is V pile prime minus VRAM prime. If we plug in what we know, we have 4.43 times an E of about a half. Velocity of the pile after is what we're looking for, minus the velocity of the RAM after. Now use parentheses here, negative 1.4. We have a negative of a negative, which is going to make those positive. And from here we'll get 2.22 minus, this becomes positive and comes over subtraction, 1.4 is equal to VP prime, which will be 0.82 meters per second after the event. And that is our best approximation for a correct answer. If we check the energy using this number, the kinetic energy after will now be 427 joules, where we started out with 2944, and that represents an 86% loss, which is not unexpected. We're pushing this pile into the ground, we're grinding it against the dirt and generating a lot of friction and heat and noise in the process. We would not expect this to be a truly elastic event with that much ground resistance. From here we could calculate the impulse as delta G, which would be G final minus G initial, where G initial is simply MV RAM. It's the only thing that was moving, which will be 300 times 4.43, which is 1330. Newton seconds are the units for impulse. Again, recall it's force, integral of force dt, so it's newtons times seconds. And G final will be M ram V ram prime plus M pile V pile prime, which will be 300 times negative 1.4. Again, these are vector values, plus 400 times 0.82, our speed from down there, which gives us negative 94 Newton seconds. And as such, we can now calculate this as G final, negative 94, minus G initial, 1330. So we get a grand total of negative 1423 Newton seconds of impulse from the ground. So that gives us an idea of how much friction and resistance that we were seeing as this thing was driven into the ground. So with that, we've covered elastic collisions, plastic collisions, and everything in between, and also looked at the impulse that we might generate and the coefficient of restitution. Thanks for watching.